All right, let's dive right in. Today, we are pulling back the curtain on our digital world to look at the very core of how pretty much everything thinks. From your smartphone to your calculator, it's a concept called combinational logic, and it's basically the secret sauce behind how machines make split-second decisions. I mean, have you ever really stopped to think about that? You punch in 2 plus 2, and it just spits out the answer, instantly. There's no tiny genius inside doing the math. So how? Well, it's not magic, I promise. It's a brilliantly designed system, and today we're going to see exactly how it all works. So here's our game plan. We'll kick things off with what combinational logic even is. Then we'll walk through the 5-step blueprint for how it's actually designed. We'll check out the essential building blocks that make it all possible, see how they team up to do math, and then we'll wrap it up with the one big idea you should walk away with.
Okay, first things first. We have to get a handle on the fundamental rules of the game here. What is it that makes a circuit combinational?
This right here, this is the absolute key to everything. A combinational circuit is kind of like a machine with a terrible memory, but in a good way. You give it some inputs, say the numbers 2 and 2, and it gives you an output, 4. It has absolutely no idea what you asked it 5 seconds ago. Its entire universe is what's happening right now. The big, flashing neon sign here is no memory. You know, one of the best ways to understand something is to look at what it's not. So on the left, you've got our combinational logic. What comes in determines what goes out. Simple. But look to the right at sequential logic. See that little feedback loop where the output can circle back around? That's it. That's memory. It lets the circuit know what happened before. So you can think of it like this. Combinational logic is the calculator, and sequential logic is the notebook. Okay, so we've got the what. Now for the how. How do you actually go from just an idea in your head to a real working circuit that solves a problem? Well, it turns out there's a very clear step-by-step blueprint for that. Imagine you're an engineer and you get a task. Let's say, build a little warning system for a car that beeps if the door is open and the key is in the ignition. You can't just start grabbing wires and hoping for the best, right? You need a process, a reliable way to get from A to B. And this is that process. It's a 5-step recipe, really. First, you just define your problem. What are my inputs? What are my outputs? Then you map out every single possibility in a truth table. Step 3 is a big one. You simplify the logic to make it as clean and efficient as possible. Then you draw it up, and finally, the most important step, you test it to make sure it actually does what you think it does. It's a proven path from concept to creation. Now, let's think about the scale of a modern computer chip for a second. We're talking millions, sometimes billions, of tiny logic gates. Trying to design with them one by one would be completely impossible. So engineers got smart and came up with a divide and conquer strategy. Honestly, the best way to think about it is like a giant, super advanced Lego kit. These are like the pre-built parts of the digital world. Instead of building a Lego car one tiny brick at a time, what if you had a pre-built engine block, a pre-built chassis? That's what these functional blocks are. They let you build incredibly complex things without reinventing the wheel every single time. It's all about working smarter, not harder. So let's meet the big three, the real workhorses of digital design: decoders, encoders, and multiplexers. Now, I know the names might sound a little technical, but stick with me because the ideas behind them are actually super intuitive. First up, the decoder. This thing is the ultimate address finder. You give it a short binary code, think of it like a zip code, and out of maybe thousands of possible output lines, it activates that one specific line. It's absolutely essential for tasks like finding the exact location of a piece of data in your computer's memory. And then you have the encoder, which, you can probably guess, does the exact opposite. Just think about your keyboard. When you press the A key, you're activating one specific input. The encoder sees that one signal and squishes it down into a compact binary code, the ASCII code for A, that the computer can actually understand and work with. And last but definitely not least is the multiplexer, or MUX for short. This guy is basically a digital traffic cop or a train switch operator. Imagine you have 4 lanes of traffic that all need to merge into a single lane. The MUX uses a select signal to decide whose turn it is. Okay, lane 1, you can go now. All right, lane 3, you're up. It's fundamental to how a CPU juggles all the data it needs to process. Okay, so we've got the basic rules down, and we've got our Lego blocks. Now it's time for the big payoff. Let's see how these simple little circuits can be put together to do something really, really powerful, like math. This is really where the rubber meets the road. I mean, every incredible thing a computer does, from rendering video games to running spreadsheets, boils down to its ability to crunch numbers. And that entire universe of calculation all starts with the simplest possible action, adding two tiny bits. Meet the half adder. This is the little engine that could of computer math. All it does is add two single bits together. So if you feed it a 1 and a 1, it has two outputs. It'll tell you the sum is 0 and that you need to carry a 1. Sounds familiar, right? It's exactly like the addition you learned in first grade. But there's a catch. That little half adder has no idea what to do if it gets a carry-in from a previous column. It's a 2-bit party only, so we need to level up. Enter the full adder. This one's a bit smarter. It has 3 inputs, so it can handle our 2 main bits, plus that carry-in from the last step. And that right there is the game changer. And this is where it gets really cool. You take these full adder blocks and you just snap them together, one after another. The carry-out from the first one gets plugged into the carry-in of the next one, and so on down the line. And just like that, by chaining these simple blocks, you've built a circuit that can add huge numbers. An 8-bit number, a 64-bit number, doesn't matter. This isn't just a theory. This is literally how your computer is doing math right this second. Okay, wow. We've covered a lot of ground. So let's just take a step back for a second and bring it all home. What's the big picture here? So let's recap. We've learned that combinational logic is the what you see is what you get part of the digital world. No memory, just instant reaction. We know there's a clear 5-step recipe to build these circuits from scratch. We saw that to build anything complex, we rely on reusable functional blocks. And maybe the most profound piece is that by linking these simple, predictable blocks together, we can achieve incredibly powerful results, like the very math that makes our computers work. This is the final thought I really want to leave you with. That tiny full adder circuit we just talked about? Imagine millions of them, all working in concert with decoders and multiplexers and other blocks, all firing billions of times per second. That isn't science fiction. That is exactly what's happening inside your phone right now. It's truly amazing how you can get such mind-boggling complexity out of such simple, elegant rules. And it leaves us with one last question to chew on. If this is the kind of logic it takes just to add 2 numbers, what incredible level of complexity is required to render a photorealistic scene in a video game? Or to power the AI that's changing our world? Something to think about. Thanks so much for joining me.